Let's take another example of total internal reflection, and that is the case of brilliance of diamond. Now you all must have observed this glittering in diamond. The refractive index, why it take place? Because we are talking in the total internal reflection. Obviously, total internal reflection must be playing a major role in this glittering or brilliance of diamond. The refractive index of diamond is 2.47. Refractive index of diamond is 2.47, so which is quite high. Just imagine refractive index of glass is just 1.5, and there the critical angle was 42 degree. Here if we calculate, the critical angle is just 23 degree. So with this low value of critical angle, we can actually cut n number of faces in diamond. And even then, we can observe total internal reflection taking place in diamond. Like in prism, we could have just that shape so that the angle of incidence should be 45 degree, more than 42 degrees. Then only we will obtain total internal reflection. But here, you have much more liberty to cut faces as many you require, because the critical angle is quite low. That is just 23 degree. Now, how does it help? It will help when you can cut as many faces in diamond. So, I would just show a ray of light traveling in the diamond like this instead of making. Just imagine that a beam of light is made incident and somehow it enters into the diamond. Then, the critical angle is just 23 degree, where the angle of incidence is much more than that. And as a result, if the face is maybe whatever, and it goes somewhere here. But again, the critical angle will be, the angle of incidence will be more than critical angle, it will go here. And again, the angle of incidence will be more than critical angle, the light beam may travel here. And again, it may travel here. You can cut as many number of faces, and you will see that in the diamond, the light beam which once enter, it just keep bouncing within. And that is something which will produce sparkle. And sometime it may come out through any side, depending on where the angle of incidence will be less than critical angle. But most of the light beam which once enter through any face will keep bouncing within it. And that's why even in small light, you will see sparkling. You will see the light beams are bouncing within the diamond. And through some face, it will come out. In diamond, the brilliance of diamond, the glittering of diamond is not just because of this. In fact, when you are talking of the diamond, there are three terms which are used. So one term is brilliance, one term is scintillation, and one term is fire. Now, what is brilliance? Brilliance is that white light which enters from the top and bounces back and exits and exit. So, brilliance is this light. It enters from the top. It just bounces back all over, produce sparkle, and then finally is coming out. So that sparkling light, that it is brilliance. Next is scintillation. Scintillation is because it has got so many surfaces. So even if the light falls on the surface, it reflects also from everywhere. So it's a light beam is quite a lot reflected also. So part of the light beam is reflected, part of the light beam which enters in, it keeps bouncing within for long. So these two, this is scintillation. And third is fire. It is like a prism also. So that fire is that when this white light, it enters in, the white light enters in, and then due to the shape of this prism, due to the shape of this diamond, you see this white light suffers dispersion that we are going to see Next, dispersion you have studied in the previous classes when white light breaks into 7 colors. So this white light breaks into 7 colors over here, and then you see this colored light that is coming out of it. This is called fire. So I am sure that when next time you are going to a diamond shop, you will not be confused among these 3 terms: brilliance, scintillation, and fire. So fire is about dispersion, white light entering into the diamond and is getting split into those 7 colors we've given. So all together decide the quality of the diamond, these 3 qualities. Now we talk of the next very important term where this total internal reflection is used, and that is optical fiber. Optical fiber, if you must have been in touch or you are reading or you are talking about communication, it is something which has brought revolution in communication. So many good companies nowadays, which are the major companies in communication, they are using optical fiber for carrying the signal from one place to other. So this optical fiber is replacing very fast the wires, and with the use of these optical fibers, we are able to transmit much stronger signals from one place to other, and that too with the speed of light. It's very cheap as compared to wires and much more effective as compared to wires. And thus the bandwidth of our communication, we are shifting from 2G to 3G and 3G to 4G and 4G to 5G. It is all only because of optical fibers. Now we try to understand what an optical fiber is. An optical fiber is something which based on total internal reflection only. Here, in an optical fiber, what is there is a optical fiber is made up of a higher refractive index medium, you can say. It is made up of a medium of higher refractive index. I just draw it like this. This is an optical fiber. It is a medium of higher refractive index. Maybe the refractive index of the optical fiber is, say, 1.7. So it has a medium 1.7. This is the higher refractive index. And this optical fiber is covered with a cladding. So this is called core. And then it has a layer at its outer surface, which is called as cladding. So this is cladding. The refractive index of cladding may be relatively low. It may have a refractive index of 1.5. So the material is of higher refractive index, the inner material, and then obviously transparent, and the surface is coated with cladding with relatively lower refractive index. Now when a light beam enters into an optical fiber, yes, it is going from air to the denser medium, it will bend towards normal. When it bends towards normal, I must say, the angle of incidence is more. The angle of incidence is higher, and the light beam which is traveling inside will bend towards normal. And once it's bent towards normal, obviously this time, the angle of incidence will be much more higher. It will be 90 NSR. So this angle of incidence I2 becomes greater than critical angle for this interface of 1.7 refractive index to 1.5 refractive index. It suffers total internal reflection. And this total internal reflection continues throughout the length of this pipe. And then finally it comes out at the other end and we can receive it. The best part is that there can be thousands and lakhs of and even much more total internal reflection that take place. But that optical signal, it never loses its intensity. With whatever intensity you get here, with the same intensity you will receive it back, because it has not been absorbed or normally reflected or refracted. It was a total internal reflection all through the path. So this is what is the functioning of the optical fiber. It's a light pipe. It can be also called as a light pipe, and one optical fiber may have just a diameter of 10 to the power minus 6 centimeter. So it's always a bundle of optical fiber that is used. So you must have seen on the roadside, there are so many thick pipes that are buried maybe 1 feet or few feet below. They are all optical fiber. They are all for carrying the signal from one place to other. It travels with the speed of light, and it is relatively cheap also as compared to wires, because it is just made up of this refractive index and nothing much. If we talk of the shape of this optical fiber over here, you can see the shape of the optical fiber in much more detail. This is the core where the total internal reflection goes on. This is the cladding. And now we don't want the cladding or the core to be scratched. So this is covered in some, strength member, in some outer jacket. So it has covering. It has covering, and this is a final outer jacket of plastic. So the central core is made up of high quality glass or silica plastic. At higher refractive index, it may have a refractive index 1.7. The core is surrounded by glass plastic cladding of lower refractive index. It may have a refractive index 1.5, 1.4, 1.3. And in order to provide safety, the core and cladding is enclosed in plastic jacket. So you can have 1 or 2 or 3 layers over the cladding so that you can protect it from scratches or from other breakage. So that is optical fiber, and it has got immense use, as I just discussed. This is how you can see an optical fiber looks like. Even if you go to a gift shop, you will see so many optical fiber. You can see like this, at the tip of every optical fiber, you can see a light signal. And in fact, if you are wishing to transfer one full image, so many optical fiber will carry different parts of the light traveling from the object, and then at the receiving end, all those images from different part of the object will together form that final image. So it is not one optical fiber that is carrying the whole image. It is many optical fiber together are carrying different parts of the image, and then finally at the receiving end, you get a final light. And these are some of the applications. The optical fiber are used for transmitting optical signal, as I told you, that even through sea or through any distance, they are carrying signal with the speed of light, and they are carrying optical signal of any signal in the form of, visible light. Like you must have studied that we are transmitting signal in the form of electromagnetic waves, microwaves, and super high frequency, extremely high frequency, very high frequency. But the visible signal, the visible light, even is of higher frequency than all of them. And that's why more is the frequency, you can do its frequency modulation much more better. So here, the optical signal is much more better to take the even transmitting signal or any information from one place to other, because it carries high frequency. It takes, it can be better modulated. It takes more clear signal from one place to other. So optical fiber, and one way an optical signal is a better signal to or better microwave or better electromagnetic wave to carry information from one place to other. And secondly, the optical fiber is a better medium to carry that signal from optical signal from one place to other, much cheaper, much faster. So obviously, as compared to other electromagnetic waves, super high frequency, very high frequency, or ultra high frequency, we would prefer optical signal. So optical signals are used majorly for transmitting the optical signals and for communication purpose nowadays. The optical fiber are used for making medical investigation. You must have studied or think of this endoscopy. Here, just imagine within your body, just 10 to the power minus 6 centimeter or very thin optical fiber is sent. It's not a problem, and you can the doctors, they can easily observe the actual problem within your body. And then in the form of they are used in the form of photometric sensors are used for measuring the blood flow in the heart. They can be very well used to understand the problems in your body, whereas they don't have to make the cuts. And then in the form of refractometries are used to define the refractive index of the liquid. And also these sensors have been used to measure temperature and pressure. So these optical fibers are very useful. They are being used in many places, and because of their small size, because of their flexibility, because of their capacity to carry the optical signal, you will see in the times to come almost everywhere around you. Now, when we talk of some more illustrations, some more examples of refraction, this is something which you must have observed. You put a pipe in water and you will see the pipe seems to be bent. How it may be happening? Just imagine, you can easily understand. Imagine there is a container and then you are putting some pipe over here or a pencil over here. But to this part, apparent depth is a real depth by mu or A mu W. Now this may be the real depth, but you will observe it has an apparent depth. Its apparent depth will be here. Similarly, for every part of this pencil or stick, the apparent depth will be less than the real depth, and that's why you'll observe as though it is bended in water. So you put anything in water, its actual state may be here, but apparent depth will be different from the real depth. So this is one example. The object appears to be inclined from its actual position. And then, now this is another example. You can see the visibility of two images of an object. So just imagine that you have a container. Container is full of water and there is a position of a fish in that. Now when from this fish, the two rays would start. One ray is say going here, one ray is say going here. The ray which is going here, this is normal angle of incidence. It is going from denser medium to rarer medium. It will bend away. Angle R. So to the person who is observing, it may appear as though this fish, these rays are coming from somewhere here. So let's take this ray to be say somewhere here. This ray is here. Here will be the normal. And once it moves from denser medium to rare medium, it will bend away. So it may be going somewhere here. So one way, this ray will appear to the person. Maybe this is the position of your eye. So to the same person, it will appear as though this ray is coming from somewhere here. So the person will observe one image of the fish from here, will observe one image of the fish from here, and that's how you can see two positions of the images, and this actual position may not be visible to you. So instead of one image, you are receiving two images because of the refraction from two different surfaces. So this is one more example of the refraction. And then twinkling of stars. What happened? The stars have their own light. So they are continuing, but they are very far off from us. Now, these stars, when they are traveling into the Earth atmosphere, the Earth atmosphere have increasing density, changing density all over. And its density is dynamic with respect to us or any person. Now, what happened that the light from the star, it may be reaching to you through different refractions. But the next moment, due to the atmospheric conditions, the density change. And this light may not be reaching to you. And next moment again, it is reaching to you. So that's how you see the starlight which is reaching to you is not constantly reaching to you. Sometimes you are receiving, sometimes you are not receiving, and that's why you see twinkling of the stars. So the light from the stars, due to atmospheric condition, sometimes it reaches and next moment it may not be reaching. And next moment again you are receiving it. So that is twinkling of the star. So it is all because of the variable atmospheric conditions and variations in the, density of the air atmosphere, because the whole atmosphere, atmosphere of Earth, these light has to pass through to reach to you. So this is twinkling of the stars. You must have seen the stars, sometimes they are bright, sometimes at once they disappear, at once they are bright, and like that. It is all because of refraction. And then this one. The sun is actually having a circular shape, spherical shape, but at the time of sunset or sunrise, you will see the oval shape. Now, why you receive oval shape of the sun? It can be explained like this, that maybe, just imagine you are on the surface of Earth, and there are different atmospheric layers above the Earth. And the sun at the time of sunset or sunrise is at the farthest, is close to the horizon. Now these sunlight, when they are traveling like this, reaching to you, and its diameter from different parts, they are traveling different distances to reach to you. So where it may be traveling a larger distance to reach to you, that part appears to be, bigger. And from the part which is where it is covering a shortest distance to reach to you, that part appear to be shorter. And that's why the sun, which is in fact spherical in shape, may appear to be oval shape, because of different part, they're traveling different distances and they're refracting differently. So this is the reason of oval shape of the sun at the time of sunset or at the time of sunrise. Another example, and that is, sometimes you'll observe water bubble in water shining a lot. Now, why it may be happening? Somewhere a container full of water, and in the inside water there is an air bubble. Now here, the angle of incidence, the critical angle is 49 degrees in water. A mu W is 4 by 3, 1.33. So if a beam of light which is falling on water has an angle more than critical angle, more than 43 degree. It will, because it is case of water to air. Now it totally reflects. And due to this, you will see this total internal reflection, it will always show this bubble very bright. So it is not only at one portion, everywhere the light beam which suffers total internal reflection will be a very bright light beam which is reflected, and that's how you will see this air bubble in water to be so shiny. And you know that condition is followed here. Angle of incidence is more than critical angle, and the light beam is traveling from dense medium to a rare medium. So this is the cause of shining of air bubbles sometime in water. And then the last point, duration of sun's visibility. Generally, it is expected that once you are on Earth, and this is horizon, this is the horizontal line, I can imagine. And if you are on Earth over here, then it is expected that once the sun is below this line, at the time of sunset or sunrise, it should not be visible. But it is not so. The reason is, even if the sun is here, much below that horizontal line, the sunlight will reach to you. And it is all because of the refraction. Just imagine, I talk of different layers of atmosphere over here. Then the light from the sun, it bend towards normal, and again it bend towards normal, and then somehow reach to you. So it will appear as the sun is somewhere here. So at the time of sunset or sunrise, when we expect the sun to be completely off, visible to us, 2 minutes extra, we can 2 minutes extra than our expectation. We can see the sun at sunrise 2 minutes earlier, and at sunset 2 minutes later than it was expected to be, not visible to us. The reason is that sunlight, it refracts through different part of atmosphere, and it appears as though the sun is still in front of us. So that's how these are so many examples of refraction, total internal reflection, and now you are in a good position to take up the numericals on laws of refraction and refraction, appear and depth, and then this total internal reflection.